All right, ladies and gentlemen, today we're going to run through the lab calculations. Now, remember, I am using sample data. This is not going to be the same as your data. Now, that's where the numbers are coming from and where your units are should be the same. However, the individual measurements and the final answers are going to vary depending on the results that you got. So I would ask, when I start pulling numbers from our data table from the lab, that you use the data that you received in the lab. Now, if at any point while we're going over these problems, you need to pause the video to get down the calculations or to recalculate to see what you would get, feel free to pause it as you're working through. If you want to go back and rewatch this after we finish up with lab calculations, feel free to make sure that you're understanding how these lab calculations and all these pieces that we've been doing fit together into our lab today. So here's what I'm going to do. We've got our data table here. I'm going to kind of be taking us through our different calculations. I'll be numbering them off to the side. What we would then do is, for the ease of data collection, you would then take the results. So for example, the answer you get for calculation number 1 goes into the first box on that big calculations table on your lab. So I'm not going to go back and do that. You guys can transfer those numbers over easy enough, but that's where those numbers will eventually end up living once you get done with things. So if you look at number 1 says, from the length of magnesium ribbon reacted and the mass per meter, find the mass of magnesium. Well, we know that we used, for my sample data here, again, your number's going to be different, we used 24.5 millimeters of magnesium in the lab. That was too small to measure directly on the balance, so we actually had to use kind of a conversion factor to figure out what mass that would be. And that actually comes from your second data point right here. We've got 1,000 millimeters of mercury equal to 1.42, think that as an equal sign, equal to 1.42 grams. Well, we've got millimeters on top right now. We put our 1,000 millimeters on bottom for every 1.42 grams on top. Millimeters are going to cancel. Looks like it's going to be 24.5 times 1.42 divided by 1,000. Again, your answer will be different because you have a different length of ribbon that you used. For me, it works out to be 0.0348 grams. Your answer will be different. Again, feel free to pause if you want to calculate yours quick and then figure out your answer. Now what we do is we take this number, whatever we end up calculating for this calculation number 1, and we pop that back into the calculations table so that we've got all of our results in a nice little grid there for us. Cool. Number 2 says, calculate the number of moles of magnesium. Well, we just figured out that we used, again, for my sample data, 0.0348 grams of magnesium. Oh, well, grams to moles? That's like beginning of the semester stuff. Grams to moles, we use the molar mass. You go to the periodic table and you find your molar mass. It's 24.31 grams per every 1 mole. Again, this is my sample data. Your results are going to be a little bit different, but this is still the same process that we're going to use to solve for our different pieces. When we take, looks like we're going to multiply and then divide by 24.31, I end up getting a really little number. 0.00143 moles. Again, that pops into the second box on our calculations table. This is really small. That makes sense. Gases take up a really big space. We are not going to have a lot of moles in our container because we were only dealing with milliliters of volume. Cool. Number 3 says, use Dalton's law of partial pressure. Let's start. What is that formula? Dalton's law of partial pressure. The total gas in a system is equal to your 2 pressures combined. In our system, we made 2 gases. We had the hydrogen gas we were making, yay! And as it bubbled up through that water, it also had some water escape in the form of gas as well. Water will vaporize as our gases pass through it. Well, if we go back to our table, look at our data table here, P total is going to be equal to barometric pressure. That was the total pressure of our system as we were conducting our experiment under lab conditions here on Earth. The pressure from just the water was this last box here. Oh, that's not so bad. Our total pressure was 750.5 millimeters mercury. We don't know the pressure from the hydrogen, so we're just going to put an X for that. The pressure from the water was 19.83 millimeters mercury. Again, you might have some slightly different numbers here. That's okay. You're still doing the same types of calculations. To solve for X, we would subtract, and you end up getting, for my sample data, 730 0.7 millimeters of mercury. But I know that millimeters of mercury is not so nice. We know we have another gas law that we're probably going to end up needing here, that ideal gas law. And we know that ideal gas law, in order for R to work, has to be in atmospheres. So let's go ahead and just change this to atmospheres right away. Now, on our little data table, on our calculations table where it's asking for your answer, it wants millimeters of mercury. So go ahead, pop this over into your calculations table so that you've got that. I'm going to go ahead and change this into atmospheres so that we're ready for the next step. It's going to save us a step here in the next part. So here's your first answer for number 3. Put that in your calculation table. But if you remember, there are 760 millimeters of mercury for every 1 atmosphere. Millimeters of mercury cancel here. Looks like to solve, we would take 730.7 times 1 divided by 760 when you do that. For my sample data, again, yours is going to be different. You get 0.961 atmospheres of pressure. Cool. We're going to need that here in just a second when we get to our ideal gas law. Because number 4 says, using the ideal gas law, calculate the number of moles of hydrogen that were in your tube. How many particles were in there? Well, we know the ideal gas law is pivot inert, PV equals nRT. PV equals nRT. Cool. Pressure of the hydrogen. Well, we just found that. That was 0.961 atmospheres. Volume of hydrogen. Oh, we found that in the lab. That one was this guy right here. But it's milliliters. In order to use a pivot inert, it's got to be in liters. If you remember, King Henry died by drinking chocolate milk. 1, 2, 3 hops. Sorry. 3 hops to get back to the base, to liters. We do the same thing with our decimal. 1, 2, 3. This becomes 0.02526 liters. Again, your answer will be different based upon the results that you got, but we would do the same process to change it into liters. We don't know our moles. That's what we're trying to solve for number 4. R we know is just a constant. Temperature. In order for our pivot inert to work, temperature must be in Kelvin. So we take our temperature, 22 degrees centigrade or Celsius, and we add 273 to get it into Kelvin. When we add 273, we get 295 for our temperature in Kelvin. There's the temperature that we're going to plug in for our pivot inert. Cool. This just became algebra, so we're going to go ahead and solve for x. Again, your number is going to be different. When I solve for my x here, I get an x of 0.00100 moles of hydrogen. Again, very, very little. That makes sense. Hydrogen, very far apart compared to its size, so it does not take a lot of particles in order to create a very large volume of gas. Now I'm going to skip number 5. You should totally be rocking number 5. Rock it. Number 6. I'm going to go ahead and just squeeze into our empty space here if that's okay. Number 6 says, from your calculations 2 and 4, what does the experimental mole ratio of hydrogen to magnesium metal look like? Well, we know that we used, for my data, again yours is going to be different, we used 0.00143 moles of magnesium. And we're making a ratio, so I'm just putting my colon here. For every, and it looks like on number 4, we made 0.00100 moles of hydrogen. Now that is an ugly ratio. All I did was take the answer from 2 and set it as a ratio to the answer from number 4. That is ugly. Ugly, ugly. So let's clean it up. We're going to go ahead and we're going to divide both of these by whichever value is smaller. In this case, it is, for me, it's the hydrogen, 0.00100. Well, a number divided by itself gives you 1. Well, I cleaned that number up nicely. But what you do to one side, you must do to the other. So we're going to divide this 0.00143 divided by 0.00100. When you do that, for me, I end up with 1.43 moles of magnesium. Now I've got a ratio that's in whole numbers, 1.43 moles to every 1.00 moles. Now I can compare that to what my ratio should have been in part or number 5 from your balanced chemical equation. And 7, you should be able to kind of think of a couple of good sources of error. Now, as you look, 1, 2, 3, 4, 5, 6, there are 6 spots on your table. Go ahead and cross out the volume of dry hydrogen at STP. Don't fill in that box. Sorry, that is the 4th box on your calculation table. Do not worry about filling that one in. But you should be able to fill in the other 5 boxes based upon what we've got going on here in our calculations. Cool. So now that you've seen the steps, you've seen the math, this is kind of how we're going to be working through our calculations. Feel free to work through, if you did not already do so, the calculations on your own lab. Once you have done that, go ahead and get the lab to the sub today, and then you're going to be working on 11.9 for tomorrow. Again, just practicing some of these calculations and these skills from the lab that we were working on from yesterday. Cool. Good luck, guys.